Hello again. What we're looking at here is a little more information about concentrations because even if you have a solution with only one species in it, like here potassium phosphate, there's more than one concentration that you can measure in that solution. And that comes from the fact that if you put K3PO4 into a solution, you can measure its concentration, 0.018 moles per liter, but when this hits water, it breaks up into its component ions, which are 3 potassium ions. We write that as K3, but I'm writing it expanded just to make the point, and a single phosphate ion. So what that means is, however much potassium phosphate there was, you're going to end up with 3 times that much potassium. Just like if you take apart 18 tricycles, you don't get 18 wheels, you get 18 times 3 is 54 wheels. The ratio of wheels to trikes is 3 to 1. In this thing, the ratio of potassiums to total compounds is 3 to 1. One of these things comes apart into a total of 4 pieces, and 3 of them are potassiums. The other one's a phosphate, which we aren't talking about right now. So you can make a ratio out of that. You can say there are 3 Ks in a single K3PO4. Let me put a number on that actually. I'll say there are 3 Ks in a single K3PO4 like this. And now they ask, well, what if we have 0.018, 0.018 moles of K3PO4? What would that mean for just the potassium? And you won't be surprised to hear we can cross multiply this. We can say 3 times 0.018 divided by 1, and that gives us a concentration of 0.054 moles per liter of just potassium, or the same potassium ions, so K plus. I guess I should have had a plus here as well. When an ionic compound breaks up, it breaks into ions, so you get these positive and negative charges appearing again. All right, so this was the amount of the original chemical, but there's 3 times as many Ks produced when this thing breaks up. Let's try that again. 0.25 mole per liter solution of strontium chloride. When this splits up, you get a single strontium ion, Sr2 plus, and you get 2 chloride ions. So for every 1 strontium chloride, you get 1 strontium. This one's going to be a little dull. They're asking about, starting from strontium chloride, how much strontium do we get? And the answer is, for every 1 strontium chloride, you get a single one of these. So in other words, the numbers are going to be identical. This is saying if there's 25 people in a room, how many heads are in that room? Hopefully 25. Those numbers are normally the same. You could write, if you really wanted to make a lot of math out of this, you could say for every 1 strontium chloride, you will get 1 strontium ion. So then, if we have 0.25 strontium chlorides, we will get X. And of course, if you multiply by 1 and divide by 1, you'll get the same result, that it's 0.25 moles per liter of strontium ions. You can do this to reassure yourself if you want to, but really no one's going to have a problem with you just writing like 1-to-1 ratio and then running with this number. It's pretty easy to eyeball it when the ratio is 1-to-1. I don't remember if that happens again. We'll see as we get through the rest of these. 2.5 mole per liter solution of magnesium acetate. I'm doing the ionic compounds a little bit fast because acetate is CH3COO, and there are 2 of them. This is also known as ethanoate. I guess the data book gives both names, so you probably figured that out without me telling you, but It's a complicated looking ion, but it's still just got a -1 charge, so it takes two acetates to match a single magnesium. And what that tells us is when magnesium acetate dissolves, we're going to get one magnesium ion and we're going to get two acetates. In other words, two CH3COO minus. So, however much magnesium acetate there is, we're going to get twice that much acetate ion. So, if we had 2.5 moles per liter of this, we could say, this thing takes a while to write out, if a single magnesium acetate produces two acetate ions, then 2.5 moles, or moles per liter, whichever you want, I have to write it out again. I'm just going to put Ma for magnesium acetate because I have no space left, over X. If you do the math, you cross multiply. 2 times 2.5 is 5, divided by 1, we get 5 moles per liter of acetate ion, twice as much as the original solution had, because every one of these is actually worth two acetates. It's like 25 people in a room, how many hands are in the room? 25 times 2 gives 50, same idea. In a 0.7 mole per liter solution of titanium 4 nitride. All right, well, titanium 4 is Ti4 plus. Nitride is N3 minus. Ooh, this thing's going to be a little wild. We need to find a number we can make using 3s and 4s, and the first number like that is 12, which means we need 3 titanium. That gives us plus 12. And 4 nitrogen. Ti3N4 is the compound. And why do we care about that? Because when this dissolves, it's going to produce 3 titanium ions and 4 nitride ions. And today they are asking about the titanium ions. A single titanium nitride gives us 3 titanium ions. So let's write that out. 1 titanium nitride gives 3 titaniums. So then, if we have 0.7 titanium nitrides, Ti3N4, how much titanium does that give us? Cross-multiplying drill again. 3 times 0.7 is 2.1, divided by 1 is 2.1 moles per liter of titanium 4. This happens routinely when you're doing other problems where we'll say, I want to get some titanium into solution, I'll use titanium nitride. You don't care about the nitride and you have no plans to use it, you really just want the titanium. And so you're thinking, based on this amount, how much titanium yield am I going to get? And you're ignoring the nitride completely because it isn't going to react or it isn't going to do anything interesting. You only care about this one piece. So, are you going to use this? Yep, pretty often. Last one. Point blah blah blah, solution of calcium hydroxide. What is this? Calcium is +2. Hydroxides are -1, so we're going to have 2 hydroxides attaching to a single calcium. The formula will be CaOH2, like so. And what that tells us is, when you throw calcium hydroxide in water, you will get 1 calcium ion and 2 hydroxides. And in this question, they're giving us calcium hydroxide, this, and they're asking about hydroxide ions. So the ratio they're talking about is 1 to 2. We can say a single calcium hydroxide, yields 2 hydroxide ions. And then they're saying, well, we didn't use 1 mole, we used 0.00108 moles. 0.00108 calcium hydroxides. How much hydroxide will we get? Answer, 2 times 0.00108 divided by 1 gives us 0.00216 moles per liter of hydroxide. Not too bad? Hopefully not too bad. If you're finding it bad, as usual, get in touch with your instructor and they will help you figure it out.